That was a very good paper. You've sparked quite a few interesting questions, and that will make this a little bit of a tough act to follow, but I'll try my best. I'll be presenting on using a meta model to compensate for datasets with different distributions. So a question I've been asking myself quite a lot lately is, what is machine learning? And it's something that most of you have probably thought of at one point or another. Well, the only real answer I could come up with is machine learning is a branch of Bayesian statistics that took on a life of its own once people realized the practical implications of this. Although it is all based off of a fundamental assumption. Previous data can be used to predict current data, and as we discovered with the no free lunch theorem, when they are random datasets, no machine learning models are able to perform well. So, one of the fundamental assumptions of machine learning is that learned models are applied to data that is identically distributed to the training data. This assumption is often not realistic. For example, data collected from a single source at different times may not be distributed identically due to sampling bias or changes in the environment. This is often problematic for practical applications, since for the sake of convenience, training data is often collected in a particular location, while the system may be deployed and evaluated more widely. This can be seen with the following two images, where the differences in distribution can clearly be seen. So deploying a model trained on the wrong distribution is likely going to give inaccurate results. On the left-hand side is where there's a change in the mean, and the right-hand side is where there's a change in variance. So to give a hypothetical example for this, if you wish to create a duck age detection system, you would preferably want to use ducks with different ages as a training set. However, it's usually quite expensive and cumbersome to create such a dataset. So, if there were 3 other datasets already available, namely a cat, a dog, and a bird dataset, it would usually be preferable to train an initial system on one of the existing datasets. So, this is what typical ducks would look like at various ages, and this is what various dogs would look like, where you can see it's fairly clear images, while cats typically have more distortions within the environment. But yet they also have specific features that are related to aging. And then, as you can see, birds also have various different species within them, and they look somewhat different. So, the question is which dataset to select. Now, the vast majority of people would select birds, and if you did not say birds, I would very much like to talk to you later because I've got no idea what's going through your head. So, the rationale behind birds is, first of all, ducks and birds look similar to me. That's something based on human intuition, where we've spent years learning things about like just general images and audio files, so people are quite good at knowing which things appear similar. Second is a dataset of birds could contain ducks, which is based on human information of what is a duck. And then thirdly, ducks share features with different types of birds, and it is unlikely to share aging features with cats or dogs, which is based on our information of what family of species a duck belongs to. So this is a fairly simple example. So, although people are quite able to predict with regards to images or audio files what is similar, they are particularly poor at predicting numeric data. So if I were to give you a data set like this, most people would just stare at me blankly, because it's very difficult to know which distributions are similar to this. To compensate for humans' inability to predict numeric datasets or how similar they are, we propose a new model architecture we call a meta-model, which trains on various metrics of the results of different trained machine learning models to predict the performance of a given model for a specific target dataset. During the training model phase, we collect the metadata used to train the meta-models by forming each possible test-train pair of datasets, and train models for each test-train combination. We then proceed to process all the features of the models trained in the train model phase as metadata. We use the metadata as features to train the meta-model to predict the MAE for a given model. As a test set, we train each model using each other dataset and apply it to the features of the unseen test dataset to create the meta features. We then compare the actual MAE to the predicted MAE of the unseen test dataset to evaluate the performance of the meta model. To generate regression datasets, we use the method adapted from Friedman and then adapted it for our custom changes. For each feature, we uniformly generate a value between 0 and 1, and for each dataset, we generated the datasets using a unique seed. We then applied the following transformations to each feature, and using the transformed features, we applied the below mathematical formula. This formula is too complex for most machine learning models to be able to reverse completely, and it then serves as a method of generating regression datasets. The main purpose of the study is to determine the following. How is the meta model able to predict regression performance? How well can it identify which dataset to use, and which changes can the meta model adjust to? To investigate the meta model's ability to adapt to change, we generated a dataset along with 10 modifications of the dataset, using the following variations to simulate changes in a distribution, namely noise, scale changes, data shifts, a combination of data shifts and scale changes, and we also test the meta model's ability to perform when using different underlying regression algorithms, and we determined how many samples in the underlying datasets are needed for the meta model to perform well. For regression dataset performance, we compared the true MAE to the predicted MAE using correlation coefficient. We used the correlation coefficient instead of the MAE or R squared, because the modifications often change the values of the target substantially, especially in the cases of additive noise and data shifts, which makes it harder to compare results directly. How well can the meta model rank a given dataset? By using the MAE, we set up two lists of the dataset ranked from the best performance to the worst performance, using the actual and the predicted MAE. We then use the Kendall-Tau test to determine the relative similarity on a scale from -1 to 1 of the two rankings. To measure the performance, we use the unmodified dataset along with 10 altered datasets using leave one out cross-validation. So, for our first comparison, we measured the different effects of adaptive noise using the following formula. Basically, it applies a greater amount of noise to each subsequent dataset. As you can see, in general the model performs well, both in correlation coefficient and for Kendall-Tau ranking. However, the more noise that gets added, the worse the meta model performs. This is to be expected since the noise breaks the correlation between the features and the target variables. For scale changes, we scaled the features during the generations of the feature step to create several unique datasets. So, as you might recall, originally all the features were generated were between 0 and 1. If you apply a scale change of 5, it would generate values between 0 and 0.2 for the first one, 0.2 and 0.4 for the second one, and so forth. Here we are primarily testing for whether the meta model can identify which datasets are relatively close to one another. The meta model is able to adapt to differences in scale changes. The greater the scale change, the worse the meta model predicts. As with additive noise, this is not unexpected, since the model is unable to reproduce the relationship completely. The greater the difference in scale, the more significant this inability to reproduce the relationship is, and the greater the difference is, as you can see with how the variance also keeps increasing. In terms of dataset sizes, the model performance is inverse to that of scale changes, i.e., the greater the number of samples, the better the meta model predicts. The meta model improves logarithmically with the greater number of elements in the dataset. For this task, we need at least 1,000 samples to achieve a correlation coefficient of better than 0.95. However, something that I would like to add that's quite interesting is that even with as few as 10 samples in a dataset, the meta model is still able to predict with some accuracy, which in my mind is a lot lower than of general machine learning problems. So, in general, the majority of the regression algorithms perform similarly. The only two noticeable exceptions are gradient-boosted trees, which has a 0.06 lower correlation coefficient, and Kendall-Tau ranking. Also, the random forest algorithm is able to rank the models using Kendall-Tau 0.03 better than models trained with any other regression algorithm. In terms of data shifts, this is similar to additive noise. However, this one just makes a linear relationship between the datasets instead of a random one, so that each dataset is larger than the previous one without changing any of the input features. By implementing data shifts and breaking the relationship between the features and the targets, the prediction performance of the metamodel is reduced significantly. Although the metamodel does seem to be able to adapt to learn some of the relationships between the datasets, the metamodel can rank the relative order better than the greater the data shift. It is still unable to learn how they relate to the original dataset. As the data shift set increases, the model is able to predict the relative MAEs more accurately. Although in absolute terms, the MAE becomes worse as the data shift increases. In conclusion, this architecture provides insight into which datasets are good proxies for a given target dataset. The meta model is able to predict the performance of the regression algorithms fairly well, and the meta model is robust and it's able to adjust to fairly substantial changes. So,